There it is. Hello. Hey everyone, this is Mr. Bob. I'm wondering if you could either raise your hand or write a quick message in the chat if you can hear me and see me. Awesome, I see hands being raised. Awesome. Excellent. So we will just, as usual, we'll hang out here for a few minutes and you can read up there the warm-up question, think about answering it maybe. It's good to see everyone. I see Owen, I see Ellie, Mitchell, Elena Keller, Alana, Alex, Gutman, Avery, Campbell, Coleman, Declan, Elena Connolly, Elliot Williams. I don't know who Freya Rappaport is. I'm curious. That name has come up before. Henry Alexander, Henry McCreary, Isabel, Katie, Leo, Lewis, Lucy, Nick, Noah Clark, Orion, Tom, Liam Tillotson, Ronan. I see all of you, or at least I see your names. Here, let me just do a little. Oh, Jaden, awesome. It's good to see you, Jaden. I'm having soccer withdrawal. I suspect you are as well. We're just going to wait for a couple more minutes. Again, good idea to have a calculator. And those other things I mentioned, and think about trying to answer that warm-up question. And we will just, we'll probably start a few minutes after 11. See if I can do some stuff here. I'm going to just experiment with some stuff here. Interesting. Okay. I'm still just trying to play around and learn this app or this program. Again, I want to emphasize the Zoom group chat. Please feel free to send messages to everyone. Also, please feel free to send messages to each other because you can do it privately as well. Obviously, just make sure it stays school appropriate. That's all I ask. And if you are having trouble hearing me, I'd love to know about that. I'm using this new headset, and I just would love to hear how it's working. So I don't have a survey for you to complete at the end of this webinar like I have with the other webinars. So if at the end of the webinar you can just give me a sense of how you've heard me this, for this time period, that would be great. Hopefully this headset / microphone works a little better than just me speaking without it, but I'm not sure. Awesome. So let's see, we're up to 33 participants. That's wonderful. I see Declan, Corinne have joined us. Welcome. Katie, Lily. I honestly don't know. I'm not sure I'm picking up everyone. It just lists you alphabetically, so I don't know who joined when. But welcome. Okay, we're going to go about 1 more minute and then we'll start. And also know that I am going to, based on some feedback, I am going to do like a 5-minute break partway through the webinar. So if people have to stretch, get up, go to the bathroom, do whatever, you can do that. A little bit about this picture, in case you're wondering. This picture is from 2012, and it basically is when Dobby, our dog, was, gosh, maybe 10 weeks old. So, and it was a funny picture because we had a crate for Dobby at that time, and my daughter decided to jump into the crate, and Dobby was outside of the crate. So I thought it was just kind of a funny little picture, and also gives you a sense of how small Dobby was back then. So anyway, okay. So it looks like we're almost ready. I'm just going to check one more thing really quickly. Okay, this will work. Okay, awesome. Okay, so let's begin, and I'm going to see if I can turn off my video because I don't think you really need to see me. Stop video, there we go. Okay, so again, welcome. This is our 3rd webinar, first one after spring break. If you haven't had a chance to look at that warm-up question, just take another 10 or 15 seconds. Do the best you can, maybe not referring to notes. If you're watching this with someone else in your family, you could also bounce your ideas off of them. My spring break was fine, given the circumstances. It's obviously a very bizarre and odd and difficult time we're living in, and we'll talk more about some things that I'm aware of. Okay, so we're going to answer this warm-up question a little later on. I do want to get right into it. So let's see. The biggest #1 reminder is this. Priority #1 is taking care of yourself and your family. I just want to keep emphasizing that. And then obviously a close corollary to that is being a good socially responsible citizen. I don't know if you've seen this term lately, but physical distancing is a better term in my opinion, and a lot of experts are starting to use it as opposed to social distancing. So please continue to practice physical distancing. I found this graphic, I came across this graphic recently, and I think it's a great example of how the impact, the actions of one person or a small group of people can have on the rest of the population. So the graphic kind of speaks for itself. I also, at the bottom of this slide, I've given you a link to the new 3 Blue 1 Brown video that came out about 4 days ago. And in that video, he goes through a bunch of scenarios, but he does it again in a way that's easy, relatively easy for people to follow. And he comes up with some big ahas, or I think he calls them takeaways. And one of his big takeaways is that if it only takes a small percentage of the general population to not practice social distancing to cause a significant impact on the rest of the population in terms of infection rates. So it's just super important that we try and get as close to 100% sort of perfection in this physical distancing, or as close as we can to it. So just keep that in mind. And again, everything else, including anything related to physics, is secondary to this right now. Okay. After webinar 2, I got some feedback from you, just really quickly. The positives: you keep saying that the narration of slides is helpful. You say that the chat function is useful. You indicate that warm-up questions are a good thing, hence you had a warm-up question this time. There was generally positive ideas about the interaction between students, or positive feedback about the possibility of doing breakout rooms. I'm going to try that today. We'll have to see how it works. I'm experimenting with it. It may not go so well, but we'll have to see. You asked for more polling questions. Unfortunately, I was not able to bring up the polling questions this time, but I will try and do it in the future. And you said since webinars tend to be longer, you recommended a short break halfway through or partway through, and I'm definitely going to try and do that. Okay, so can everyone just raise their hands? I just want to make sure I'm not talking to no one. Okay, cool. I see a bunch of hands going up. Awesome. All right, let's keep going. So I want to talk about some recent news, some recent information I've received both from the IB organization via Jennifer Wyatt, and also regarding at the moment what the grading policy is in terms of assignments. Then I want to talk a little bit about Flipgrid. We'll do a little bit of review from last class, and then we'll share new information. We'll go through some new slides. We'll talk about Hubble's law, and we'll also talk about cosmic microwave background radiation. And I doubt we're going to get to dark matter today, but we will save that for next webinar, which will be Thursday. Okay, so let's get right into it. Okay, so right now I'm talking to those of you who are testing, so to speak, who are either full diploma students or you signed up to take either HL or SL IB physics test this spring. So all the information I'm providing you is what's been provided to me by Ms. Wyatt, and Mrs. Wyatt has received this information from the IB organization. So the big picture things you should be aware of, and you probably are already aware of, but I'll just reiterate it, is that there are not going to be any external assessments, in other words, sit-down exams this spring. Normally there's a 3-week period where you take those exams, those 3 exams for physics and other subjects. That's not going to happen, okay? The other big difference that we just learned about is that every single IA that was submitted to me, I need to submit to Mrs. Wyatt, to submit to the organization, because they're going to actually score each one of them. Let me back up and give you a background on how this usually works. Typically what works with the IAs is that I submit just scores to the IB organization via Ms. Wyatt. And then the IB organization comes back and says, okay, send us these 8 papers. They usually ask for a small sample of what I've scored. Then they send that to assessors. They grade those papers. And if there is a significant persistent difference in how they view the score on the paper versus how I graded it, all of my scores for all of the students can get moderated up or down, meaning they might lower everyone's grade on the IA or raise everyone's grade on the IA, depending on what they find. This year, they have decided, no, they're going to actually individually grade. IB assessors are going to individually grade every single IA. So I will be submitting those to Mrs. Wyatt here in the coming weeks. And then the third point, and this one I'm just going to give you what I saw from IB, and basically from the IB letter, taken from the IB letter, and I really don't have much more to offer you on this other than what they say here, and I'll just read it out loud. It says how the final results will be calculated. Quote, we will be using vast historical assessment data to ensure that we follow a rigorous process of due diligence in what is a truly unprecedented situation. We will be undertaking significant data analysis from previous exams, individual school data, subject data, as well as comparative data of schools who have already completed uploading requirements and those who have not. End quote. I got to be honest with you, I have very little idea of what that means. All I know is that I need to submit all of the IA grades and all of the actual copies of the IAs you submitted, and they are obviously going to account for that with all the other stuff they said there to come out with an IB certificate grade for each student. So Mitchell asked a question, do you know if the score we have already been given for the IA will factor into the final score? Yes, I'm confident in saying that the IA score that you receive from the IB assessor will impact your final grade. Whether what the grade that I provided you on the IA impacts the IB assessor remains to be seen. I would like to think that it would, that if I score someone a certain score and a first IB grader doesn't agree with me, that then the paper would go to be graded by a second IB grader just to make sure that they're that a student doesn't get you know, unfairly treated. But I honestly have no idea for sure. Are there other questions? If you want to put them in the chat box, I'm happy to answer them now or later. If you have individual circumstances that you want to bring up with me, please do that separately, not in the context of this webinar. You can send me a remind.com. You can send me an email, and I'm happy to have conversations with you. I know Mrs. Wyant is also happy to have discussions with you and your family as you see fit. So that is what I know about IB in terms of IB grading. Let's move on to Cleveland High School policy. Oh, Alex Gutman just asked, are we still going to have an IB type test for this class? So here's what I will say. Well, Alex, you know what? Let me answer that after I give you this next slide, because that'll give some clarification to that. Okay, so if you look at this next slide, now we're talking about grading policy within Cleveland High School / PPS for second semester. And the answer is, there's a lot that's still unknown. PPS has no idea yet how second semester grades will be determined. They are awaiting guidance from the Oregon Department of Education. Having said that, we have been given some guidelines in the meantime, and they basically say this. Any assignment with a due date after the closure date, March 13th, will not be graded in Synergy, okay? So any assignment that I provide to you after the closure date will not go into Synergy. The previous assignments prior to March 13th can be graded, and I have graded some of them, and if you submitted some late, I will still grade them as I have time. I do want to do a special shout out to those students who took the Fields quiz on Thursday the 12th, okay? And some of you have asked me questions about that. Here's what I want to say to you. If you took that Fields quiz the day before we closed schools, then just know that at some point in the future, and I can't tell you when because things are very crazy right now, I do plan to score it. Okay, it could be weeks from now. But my promise to you is this. If you did poorly on that Fields quiz and me entering it into Synergy would lower your grade, your percentage grade, I will not enter it. If you did well enough on the Fields quiz that me entering it into Synergy improves your grade, then I will enter it. Okay, so please keep that in mind. Okay, so to answer Alex's question, Alex, are we still going to have an IB type test for this class? I'll answer that in two ways. If your question is, will the IB organization offer an exam where you sit down at some point in the future and take an exam on IB physics? The answer to my understanding is no. They've canceled those exams and there are no plans to reschedule them. If your question is, am I going to give a final, like a second semester final for this class? I will tell you that a lot of that depends on whether we ever go back to school this school year. And obviously if we don't, and that's a big TBD, I would say. And again, it depends on what happens with Oregon Department of Education and what guidance they give to PPS and what guidance PPS gives to the schools. Okay, so please know that while you are not in class, not physically in class during this time period, the firm guidance we've been given is that we cannot put grades in Synergy. In other words, we cannot grade you, assess you in terms of work completion or what you know of the material that is being presented during this closure time. Okay, so should we still be doing the IB review that you post on Google Classroom? Okay, Nick, I'll answer that with the next slide here. Let's go to the next slide. So let me go to this next slide, then I'll try and answer more questions. So here's my plan, okay? My plan is to continue doing twice a week webinars, okay? The next one is Thursday, this Thursday at 11 a.m. I am going to continue to assign problem sets and online investigations like those PhET labs. And to the extent that your home circumstances allow you to, I would suggest that you try and do them and continue to learn. Why? So again, you're not required to complete the work. Your current Synergy grade will not suffer if you don't complete it. But then the logical question might be, why would a student choose to do work if it's not going to be graded? And I'll give you a couple of reasons here. Colleges might require you to take a placement exam to determine if you receive credit in the course, especially once they get wind of what the IB organization is doing and AP organization is doing. They might put more weight on those placement exams. And also, if you think about it, at some point you are probably going to take a physics class in college. A lot of you are. And the more that you can learn during the spring, i.e. by doing the activities that I give you, the better off you'll be when you set foot into that environment. The second thing I just want to emphasize is that, you know, and this is not meant as a menace. I always try and write the strongest possible letters of recommendation for students. But obviously, if I have a student who has continued to really put forth a good faith effort during this time to do the assignments, to learn, basically, you know, I can talk about that in a letter of recommendations I write for a student in the future. So just keep that in mind, that, you know, your actions at all times sort of reflect on your character, and for positive and negative. And so, again, to the extent that your family's personal circumstances allow you to participate and accomplish these assignments, they can only help you in that sense as well. And then finally, you know, and it might sound a bit romantic at this day and age, especially given the current circumstances, but I do believe that there is a value, a big value, in learning just for the sake of deepening our understanding of our complex and fascinating world. So let me just scroll through the chat function and see what we have. Nick Brink asks, should we still be doing the IB review you post on Google Classroom? And again, for the reasons I just laid out in this slide, I would suggest that to the extent you can, yes, you should try and do the IB review. But if I had to put a hierarchy on it, if you have limited time, I would say those IB review packets that I'm putting on Google Classroom once a week, those would be lower priority than, say, the webinar activities, the pre-webinar activities I'm suggesting you do, and the problem sets that I'm going to keep putting on, and also the sort of online labs that I'm going to be offering to you in the near future. So IB exam review, I would say those packets are the lowest priority. So Leo asks, our grades are unchangeable. At the present, your grades are unchangeable, except for if you have not submitted work that was due before March 13th, and you want to submit that work and you want me to grade it, I will still accept that. So that would allow you the ability to possibly raise your grade. Now, again, I said at the present, your grades are unchangeable. That could also obviously shift depending on what happens. ODE might provide some direction to the district in the coming weeks. And also, I can imagine a scenario, it seems a bit unlikely at this point, but I can imagine a scenario where maybe we reconvene school for a few weeks in June, for example. And at that point, if we reconvene school for a few weeks in June, you know, there could be assignments at that point that could change your grade. So those are my thoughts at this point. I'll give you about another 30 seconds here if you have any other questions that you want to post in the chat room before we move on. That's what I know. I will tell you again, if you have very personal questions, personal circumstances, that I'd ask you not do that in the group chat, that you then send me a remind message or email me separately. And again, I just want to emphasize that Mrs. Wyant is working very hard and advocating on Cleveland's behalf with the IB organization. So please keep in mind that she's doing all she can in terms of making sure that we get treated fairly by IB. Okay, I don't see any further questions in the Zoom group chat, so I'm going to keep going. Okay, and oh, that's right. The last reason why you would want to do work is because who doesn't like space practice? I hear it's out of this world. Ha 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 ha. Okay, Flipgrid. Those of you who used Flipgrid, thank you so much. Those of you who actually did the assignment, if you created that video, I so appreciate it. I have to tell you, I got choked up as I watched some of them. It was so great to see you and to see you just talking for a minute. I know this sounds really corny, but I just have to tell you, social isolation works in all ways. It's not just students with each other, but teachers really enjoy that interaction with students. Hopefully that's why a lot of us are in this business. And so it's really wonderful. Later on, you're gonna have a chance to brainstorm with classmates about how to maybe use Flipgrid a little bit more. So keep that in mind. And between now and the next webinar, if you didn't do this yet, please go back and post a video of yourself if you haven't done so yet, and watch classmates' videos. I would suggest watch at least 2 classmates' videos and try and give them a positive vibe check. Get it? Positive vibe check. All right, let's do it. Flipgrid. Okay, let's go back to the warm-up question. Differences between type 1a and type 2 supernovae. Hopefully you were able to list some or all of these differences and just very quickly rattling down them. Remember, the type 2 is that massive star, that classic supernova that we think about. The type 1a is really formed in a binary system where one white dwarf cannibalizes another one until it goes above that critical mass and becomes material to become a supernova. The type 1a has the predictable peak luminosity, which allows it to be used as a stamped candle, whereas the type 2 does not. And then the type 1a does not have any hydrogen lines in the absorption spectra, and the type 2 does. Okay, so let's keep going. I have 3 more questions that I want you to review, to look at, discuss, and review. And I won't read them out loud. You can see them there, but please go ahead and take the next 45 seconds to either talk about it to yourself, if you're watching this by yourself, or if you're watching it with a family member, which I understand some families are, please discuss it with your family members. Let's go. 45 seconds on the clock. Begin. Whoops, sorry about that. About halfway through the time, got about another 20 seconds. Three, two, one. All right, let's start going through these. So the first one, how is cosmological Doppler shift different than conventional Doppler shift? Well, basically, the best analogy I can give you is, again, the analogy we talked about and was in that video. If you and your friend are standing on a sidewalk, the conventional Doppler shift is the idea that either you or your friend are moving away from you. So in other words, there's some sort of relative motion between you and your friend, either towards each other or away from each other. And that's going to cause some sort of frequency shift. It could be either towards the blue end or towards the red end of the spectrum. Cosmological Doppler shift is different. Even if you and your friends stay still, there is still going to be a Doppler shift in the light waves leaving your friend and coming towards you, because the sidewalk itself between you and your friend is expanding with time. And so those light waves from your friend to you will be redshifted, okay, because they are moving away from you. All right, the next question. What are the 2 stunning discoveries Edwin Hubble made in the 1920s? 2 things. One is that nearly all the galaxies are redshifted, meaning that they're all moving away from Earth. And the other one, which is huge, is that the further the distance between the galaxy and the Earth, the bigger the redshift was. These are 2 monumental ideas that came into our sort of understanding in the 1920s. Okay, and the third one, what is the stunning discovery that 2 teams of scientists made in the 1980s about the current rate of expansion of our universe? And that is the fact that the rate of expansion between the distant galaxies is accelerating. Galaxies that are distant from each other are moving faster and faster away from each other. And we don't know much why. And the reason we don't know much why is because it's very difficult to detect whatever's doing it. And so we call that thing that's doing it dark energy, but we really know very little about it. The analogy that is a good one to keep in mind is that it's like you're at the surface of the Earth, you heave a baseball straight up into the air, and instead of that ball slowing down over time because the gravitational pull of the Earth is kind of pulling away, tugging at it, so to speak, it moves faster and faster as it moves away from the Earth. I do want to point something out that Dr. Filipenko talked about in his TED Talk, and it's important to keep in mind, and that's this. You may want this expansion of the universe to continue because, let's say, for perhaps you're really sick of your sibling that you've been around for a lot recently. So don't think that like next week you're going to be far away enough from your sibling that you won't be able to hear them. okay? In your local galaxy, in your local solar system, the force of gravity still is the dominant force, okay? It far and away is more dominant than this dark energy. But what we are observing, cosmologically speaking, is that across the vast distances between galaxies, if you compare one galaxy and another galaxy that's very distant away from it, that rate of expansion is accelerating. They're moving away from each other faster and faster over time. And so in that case, the dark energy sort of force, if you want to call it that, I hesitate to use that word because we really don't know, is outweighing or outmuscling gravity, so to speak. Okay, so that's the review. So let's keep going. The new information I want to talk about today is Hubble's law, cosmic microwave background radiation, and dark matter. So let's get into it. Actually, we probably won't get to dark matter. That'll be for next time. All right, we do have a humor point number 1. You guys ready for this? All right, the question is, what is another name for a supernova? What's another name for a supernova? Well, it's a pop star. Haha, haha, get it? Pop star. Supernovas kind of, sort of, you know, they explode, pop. You know, it's really hard. I must say, the one thing I miss about, more than anything else about being with you all, is hearing the roaring laughter from the classroom when I put these jokes out. So anyway, I guess I'll just have to deal with that. I know, Avery, I don't have the laugh track today. Okay, let's keep going. What did Hubble do? Let's make sure we understand what Edwin Hubble did. And I think I explained this briefly last class or last webinar, but I want to go a little bit more into it. So if you see these dots, it's quite simple. What he did is he basically measured the distance to faraway galaxies, and the Cepheid variables, the work of Henrietta Leavitt and the Harvard computers was vital to this. He measured the distance to these faraway galaxies, okay? Then separately, he measured their recessional speed using the size, the Doppler shift he was observing. Okay, recessional speed means speed with which you're moving away. And so notice on the x-axis, he plotted the distance, and on the y-axis, he plotted that speed. And those dots you see there are the dots, is how the data lined up. And so that's where we get this idea called Hubble's law, that there is a direct sort of a proportional relationship, a linear relationship between the distance between galaxies and the speed with which they're moving away from each other. Okay, it's interesting to note when Hubble originally did this work in the 20s, his value for this slope, what we call the Hubble constant, which we're going to talk about more here in a second, his value was 500 kilometers per second per megaparsec. Okay, notice today, this is pretty close to the best value, or the best estimate. This is in the range of the best estimate we have today. It's around 71 kilometers per second per megaparsec. And I'll explain more what that means in the next slide. Okay, so let's go to the next slide. So here is Hubble's law in equation form. It's quite straightforward in equation form, as you can see, and it's basically a graph of the data. Remember, y equals mx plus b, right? So if I take the distance between galaxies, put it on the x-axis, and plot their recessional speed on the y-axis, and if I get a straight line, then the slope of that line is something we call Hubble's constant. Okay, so the d is measured in megaparsecs. The speed is measured in, it's the recessional speed, it's measured in kilometers per second. And h is known as that Hubble's constant. And right now, the best science we have puts its values somewhere between 67 and 74 kilometers per second per megaparsec. I suspect a few of you are saying, what is up with those units, Mr. Bob? How are we supposed to interpret them? Let me tell you. So think about it this way. Let's back up. Remember, a parsec is about a little over 3 light years. A megaparsec would be a little over 3 million light years. Okay, so if I look at a galaxy and it's just 3 million light years away from our galaxy, the Milky Way galaxy, then its speed with which it's moving away from the Milky Way galaxy is going to be right around 70-ish kilometers per second. If I compare that to another galaxy that is 2 megaparsecs away from us, then its speed with which it's moving away from the Earth is going to be about 2 times 70, so about roughly 140 kilometers per second. So in other words, for every megaparsec that a galaxy is away from the Earth, its recessional speed gains about 70 kilometers per second. Okay, so with that in mind, we have to realize that Hubble's law has really significant limitations. The first one is this: the fact that we call it the Hubble constant is kind of a misnomer. Some people call it the Hubble parameter, because even though we can fix a value for it now, here in our present time, we have pretty good evidence to suggest that over the time period that the universe has been expanding, that rate of expansion has changed, okay? There's good evidence to suggest it expanded faster earlier in the universe. And again, there's even evidence today that that rate of expansion is being messed with by dark energy. But the other thing I want to make sure you understand is that there are significant uncertainties in the Hubble constant, because it's quite difficult to accurately and precisely measure the distances to these remote galaxies accurately, despite our best technology. In fact, there are huge debates that have occurred over the years related to this constant, and actually there still are occurring today. In fact, in that red little asterisk, I'm giving you a preview of one of your suggested assignments before the next webinar. There's a wonderful article that came out in the Scientific American in March of 2020, most recent issue, and it explores this sort of raging debate within the scientific community, within the cosmology community, about the measurement of the numerical value of Hubble constant. So you will get a chance to look at that. Okay, let me just see if there's anything in the chat function before. Okay, it looks like we're good. All right, so I do want to walk through a problem with you, and let's go ahead and do this one together. The problem says, determine the maximum upper bound age of the universe using the Hubble constant. Provide your answer in years. Assume the Hubble constant for this problem is assumed to be 72 kilometers per second per megaparsec. Okay, so let's look at this. We know from Hubble's law that, whoa, that is not, let's back up. Okay, all right, there we go. I almost gave away the whole answer. We know that Hubble's law says that basically that the speed and the distance of a recessional, the distance between galaxies and the speed, the recessional speed, are directly related. We also know way back from first year physics that speed is distance over time, right? So what we can do is we can set these equal to each other because they both equal recessional speed. So if I do that, if I say d over t equals h times d, what do I get? Well, notice that the, hold on, let me do something here. Change the color, can I do that? Yes. Notice that the d's cancel. So what am I left with? I'm left with this idea that 1 over time equals the Hubble constant. So if I solve for time, I can basically get this relationship. Time is 1 over h. And so in other words, what we're implying here is if I take the inverse of the Hubble constant, I can get a rough estimate of how old the universe is. Okay, let me say that again. If I take the inverse, because again, you have to think about this. If we know the rate of expansion of the universe right now, then we can kind of play that tape in reverse. We can rewind it and say, well, if I work backwards then, I can know at what point was everything basically all together in that singular point that we call, you know, the start of the Big Bang. So let's do that. So for our purposes here, this is 72 kilometers per second per megaparsec. So this means time equals 1 over 72 kilometers per second per megaparsec. Okay, now this is going to be a huge factor label problem because what I want to do is I want to change this to years. So let me start all the way over here on the left. So if I have 1 over 72 kilometers per second per megaparsec. Okay, that's the same as saying, I'm going to take the seconds to the -1, megaparsecs to the -1, I'm going to put them on top, because I can do that with units just like I can do it with numbers. So that would be seconds, megaparsec is on top, and 72 kilometers is on the bottom. Okay, so now we just have to basically convert all this to years. So let's just walk through this. All right, so we know a megaparsec, or a parsec is 3.26 light years, right? So 1 megaparsec is 3.26 times 10 to the 6th light years. Okay, so these cancel out, these units cancel out here. Awesome. So let's keep going because we have to get to years. So we know light years is what? A certain number of meters, right? 1 light year is 9.46 times 10 to the 15th meters. This is all in your data booklet. I'm not giving you anything that you wouldn't be able to look up in your data booklet. Okay, so that gets us into meters. Meters on top, kilometers on the bottom, so we have to convert. So remember, 1,000 meters is 1 kilometer. Awesome, so that cancels these out, and that cancels these out. And so I've actually got units in seconds, so I just have to convert from seconds to years. Okay, well we know, let's see, 3,600 seconds is 1 hour. That cancels that out. We know there's 24 hours in 1 day. And we know there is 365 days in 1 year. So notice I have just labeled my way into knowing, converting the Hubble constant into a certain number of years. So I'm going to pause there and give you about half a minute there to just crunch this on your calculator and see what number you come up with. And I'm going to check the chat room while you're doing that, just to see if there are any questions I can answer. Alex, wonderful job ruining it for everyone. Good job, Alex Gutman. Just kidding. Okay, I'm going to calculate this myself. Okay, so when I crunch through these numbers, I get a number that is, up here, 1.36 times 10 to the 10th years. Okay, and that's the same thing as saying 13.6 times 10 to the 9th years. And we know 10 to the 9th is billion. So this is 13.6 billion years. All right, so there's a high-pitched noise in the background of my audio. Is everyone, give me a thumbs up. What do I want to say? Oh, you know what? I wonder if it was when I was writing on the tablet. Do you still hear the high-pitched noise, or was it just a few minutes ago? Give me a thumbs up. Raise your hand if you can hear me okay without a high-pitched noise. Okay. Okay. I think I know what it was. I think I was writing on my tablet, and maybe that was causing it. I'll have to keep that in mind. Okay, so it sounds like everyone can hear me okay now. If you can't, please let me know in the chat box. Okay, so notice after this calculation, what we get is we get approximate age for the universe. That's pretty darn cool. I think so. There are some limits to this, okay? The first one I just want to emphasize is this. This is an upper limit, okay? Because we have pretty good evidence that the universe expanded faster at the beginning. And if it did expand faster, then the actual age of the universe could be slightly younger than what we get using the Hubble constant. And the bottom bullet there, I just want to emphasize that this is still very much an open question. The best science we have now suggests that our universe is somewhere between 13.6 and 14 billion years old. I'm sure you could look up recent studies and it would narrow it down to even further to like 13.8 plus or minus like 20 million years. But it is still very much an open question. And again, this article that you're going to read will give you a better sense as to why it's an open question. Okay, so how are we doing on time? All right, I want to get you in your breakout room, so let's see if we can get there. All right, this is the article teaser. I'm not really going to say much about it other than just to say, if you look here, do you see how down here, one technique to measure the age of the universe, excuse me, to measure Hubble's constant, this orangish technique, notice, and this purple technique, they're different ones. And way back in 2000, there was pretty much a lot of agreement. And so the expectation was, as we got more and more sophisticated equipment, that we would just continue to have an agreement between these two methods. But notice what's happened since 2000. This purple method has gone in one direction, and notice these are the error bars associated with these measurements. So they've gotten better, more precise, both the purple and the orange, but at the same time, they've started diverging, and that's a problem. So again, that's a teaser for the article. You will, I believe, if I'm not mistaken, we were at this slide. And just to recap very quickly, in the 60s, you have these physicists who are basically saying there's more helium in the universe than can be produced by stars. This means we suspect in the early universe the conditions for fusion existed. If we had fusion in the early universe, then there was electromagnetic radiation created because of that fusion. And that electromagnetic radiation would have then been traveling across the universe as the universe expanded. And as it traveled across, its waves would have been redshifted as well. And the calculations are such that in the present day, that radiation would present itself as that of a black body that has a temperature of about 2.7 Kelvin. So what we're going to do here is we're going to do that calculation very quickly. All right, I don't need to see myself. You don't need to see me. So here we go. In what region does that EM spectrum belong to? If I have a black body emitter at 2.7 Kelvin, what we're going to use Wien's law. So that says that wavelength, max wavelength times temperature is 2.90 times 10 to the negative 3 meters Kelvin. And so if the temperature is estimated to be 2.7 Kelvin, and this is 2.90 times 10 to the 3 meters Kelvin, then if you do this calculation, you come out with something that's just a little over 1 times 10. This is 2.7 Kelvin. This would be 1.0 times 10 to the negative 3 meters. All right, where is 1.0 times 10 negative 3 meters on the electromagnetic spectrum? It's right here in the microwave range. And so these Princeton physicists, I think they were Princeton, I can't be sure. They basically proposed this, okay? About the same time, not too far away from them, no more than about an hour's drive away from them, were these two Bell Labs engineers. And there they are right there. They have this huge, huge telescope, okay? And this telescope is meant to collect not visible light, but microwave light, okay? And they have this noise, this fuzzy noise coming in on this telescope, and they do everything imaginable to try and get rid of this fuzzy noise. They think it's bird poop. They think it's a bunch of things. They try and weed it out, and eventually they come to realize that, hey, we can't get rid of this noise. What is going on? Okay? So, so what happened was, they discovered that it's not only steady, but it's also isotropic, okay? Meaning it's in the same in every direction. So it's coming the same in every direction, and it's steady. And so in the end, what they discovered is when they talked to the theoretical physicists, they realized that this is the microwave background radiation that was predicted by these models, okay? And so that was the suspicion. But we didn't have data to support it. So in the 70s, something called the Cosmic Background Explorer was basically created. It was a project of NASA to send this satellite out to measure this, to closely measure this microwave background radiation. I just want to point out that from 74 to 89, This is like 15 years, right, for this to be launched. But when COBE came back and COBE actually started taking data, this next slide is just beautiful. And here it is. These dots, or this line here, this continuous line is what the theoretical physicists' theoretical equation predicts for what should be the microwave background radiation, how it should look, how its distribution should look. These little rectangular, or excuse me, square data points is the actual data from COBE. So isn't this amazing? The theoretical line and the actual rectangular data, I mean, you cannot ask for a more precise match of the two, of theory to sort of experimental data. It's just phenomenal, and it gives me goosebumps every time I look at this. So, so in the late 80s, early 90s, we had our first experimental evidence to suggest that, or really more precise experimental evidence to suggest that cosmic microwave background radiation really exists, and it does lend evidence to this idea of a Big Bang. Since then, there have been two other, WMAP is another satellite, and then Planck is the most recent one, and they have just reconfirmed with even greater precision. So this is evidence of the Big Bang, because this basically shows that, again, this cosmic microwave background was formed a few 100,000 years after the Big Bang. So it's early in, after the start of the universe. And since then, it has cooled to a faint whisper, okay? It's cooled for approximately, our best guess is 13.7 billion years, okay? And it's caused that radiation that's originally produced in the Big Bang to be cosmologically redshifted. So this gives another piece of evidence to the Big Bang model that at some point in the past, our universe was concentrated in a very incredibly hard to understand sort of single point. Okay, so a couple things about CMB that I want you to understand. It's isotropic, meaning it's got pretty much the same value in every direction. It models that black body emitter that we talked about. The third and final thing is that there are what we call small anisotropies. These are small fluctuations, and these tiny fluctuations way back in the early universe is thought to be the seeds of the clumping of matter into what we know today as galaxies, stars, and planets. Okay, so let me just look at the chat room really quickly. So Elena asked a question, if 13.6 is the upper limit, why is it predicted between 13.6 to 14? Remember, the sample problem I gave you assumed a Hubble constant of 72, but that number is actually got a range of 67 to 74. So there's uncertainty in that number, and that's why the upper limit of 13.6 is not a hard upper limit. That is just one of the possibilities based on, it depends on what number you pick for the Hubble constant. Okay, so the last part, 2 more slides, and we're gonna do a little bit of breakout room action. Cosmic microwave background radiation, okay, is the same thing as 3-degree Kelvin background radiation. And it's also the same thing as what they call microwave background. So if you see any of those terms, they're basically talking about the same thing in any sort of book or website. Okay, so last slide here. I just want to formally kind of present the Big Bang model and then kind of summarize the evidence around it. So this is the most broadly accepted theory for the origin and evolution of our universe. And it suggests that approximately 13.8 billion years ago, the portion of the universe that we see today was concentrated in that single spot. And since then, the universe has expanded from that incredibly hot, dense state into something much cooler that we recognize today. So that's what we call the Big Bang model. It's got a lot of support to it, and I'm going to kind of summarize the support in this next slide. So 3 big things you want to think about when you think about describing the body of evidence that supports the Big Bang. First is the fact that all galaxies are redshifted. We've talked about this, right? If all galaxies are redshifted, then it was all once smaller and concentrated in a single point, and it must have started expanding after that. The second thing is what we've just been talking about, that microwave background. This is evidence of a hot universe that cooled as it expanded. And the fact that the COBE and all the other experimental data so precisely agrees with theoretical physicist equations is stunning and provides quite strong evidence to support the Big Bang. The final and third piece, which I don't really have a lot to share with you about, I do give you a link there if you want to explore it some more, is that other equations that model the Big Bang suggest a certain abundance of helium and hydrogen in the universe. About a quarter should be helium and about 73% should be hydrogen. And so far, our observations support this. The helium abundance is in accordance with what we would suggest from the Big Bang. Okay, so here's what I want to do. I would like to take a quick 5-minute break. I realize that some of you may need to break off or like stop the webinar. If you do, that's fine. But I do want to recommence in a few minutes at 12:02. And I'm going to be creating some breakout rooms with the participants here. And I would just love for you to experiment with the breakout rooms. So I'll give you instructions here in 5 minutes. I actually have to go in the next 5 minutes and create the breakout rooms with the people who are here participating. So we will reconvene at 12:02 and spend about 10 minutes in the breakout rooms, and then we'll call it good. Okay. The 5 minutes has commenced.